Math 1143, section 3.3, logarithmic functions. We're in the middle of objective 4 on graphing logarithmic functions. So we started to graph this one by identifying some ordered pairs and using properties of logarithms. So let's see, the next power of 2, if I pick x to be 7, 7 minus 3 is 4. So if I pick x to be 7, then log base 2 of 7 minus 3 is log base 2 of 4. But log base 2 of 4 is 2. So the y value is 2 when the x value is 7. And then I think we can go ahead and sketch the graph. We have a vertical asymptote at x equals 3. So we observe where the vertical asymptote is. It's the vertical line x equals 3. And then we'll plot a couple of these points. The point 4, 0 is the x-intercept. And when x is 5, the y-coordinate is 1, so 5, 1. And when the x-coordinate is 7, the y value is 2, so that's 7, 2. And the graph will look something like this. So knowing how logarithms work and then picking x values based upon what the base of the logarithm is can help you find integers for the y values. Okay, so now let's find the inverse. So find the inverse. So in step 1, we write y equals log base 2 of x minus 3. Then in step 2, interchange the x and y. So we write x equals log base 2 of y minus 3. And then we solve for y. Well, there's just a little bit more to do on this one than in the previous one, but it's not too bad. Convert this logarithmic equation to its exponential equation equivalent. So 2 to the x equals y minus 3. So we'll just write y minus 3 equals 2 to the x. And then just add 3 to both sides. So we get y equals 2 to the x plus 3. So make sure that the plus 3 is not in the exponent. And so this function, y equals 2 to the x plus 3, and this function, y equals log base 2 of x minus 3, these are inverses of each other. So I'll just note that those are inverses. Okay, in the next exercise, we'll just find domains and inverses without graphing. Okay, so for f of x equals the base 5 logarithm of 3x plus 6, find the domain. Okay, so the argument on this one is 3x plus 6. So 3x plus 6 has to be positive. And so that means 3x has to be greater than negative 6. And then divide both sides by 3, x is greater than negative 2. Okay, so the domain in interval notation, if it's greater than negative 2, it's parenthesis negative 2 comma infinity. Whoops. Sorry about that. It's parenthesis negative 2 comma infinity. That's the domain. Now let's just find the inverse. So step 1, replace f of x with y, so y equals log base 5 of 3x plus 6. Then step 2, replace y with x and replace x with y, so we get x equals log base 5 of 3y plus 6. And then we solve for y, but what we do is write down the exponential equation equivalent to this logarithmic equation. So the base number 5 raised to the power x equals 3y plus 6. So I'll just write 3y plus 6 equals 5 to the x. And then we can solve for x in a couple of steps, or solve for y, in a couple of steps. First, subtract 6 from both sides, so we get 3y equals 5 to the x minus 6. And then divide every term on both sides by 3, and we can just write y equals, this is going to be what f inverse is. F inverse is, in the numerator, 5 to the x minus 6, and all divided by 3. And that is good enough for our purposes. Okay, the next one, g of x equals the natural log of 5 minus x. So to find the domain, we say that the argument has to be greater than 0. So 5 minus x is greater than 0, which means negative x is greater than negative 5. And then if you divide both sides by negative 1, then x is less than 5. So the domain is all real numbers less than 5. So that's from negative infinity to 5 parentheses. That's the domain. Now we'll just find the inverse. Replace g of x with y. So y equals the natural log of 5 minus x. In step 2, replace y with x, replace x with y, and then proceed to solve for y. So the base of the natural log is e. So that means e raised to the power x equals 5 minus y. So I'll just write 5 minus y equals e to the x. And we can get the inverse in the next step if I just add y to both sides and subtract e to the x from both sides. Add y to both sides, subtract e to the x from both sides, I get y equals 5 minus e to the x. And that's the inverse. That's good enough. Oh, we should call it g inverse of x equals 5 minus e to the x. Okay, and the final problem, use logarithmic functions in applications. So the value of an investment of $7,000 increases to $11,000 in 9 years. Find the annual interest rate, R, if interest is compounded continuously. Okay, so let's first write down the function. $7,000 is invested initially, so the value, if the interest is compounded continuously, is 7,000 after t years, 7,000 times e to the r times t. Okay, we don't know what r is, but this is just for any number of years t. But then we'll use the information given. We're told that the value v is $11,000 when t is 9. So we'll replace v with $11,000 and set that equal to 7,000 times e to the 9r. All I did was replace t with 9 because we're told that in 9 years the value is 11,000. Okay, so we're going to solve this equation for r. First, divide both sides by 7,000, and note that 11,000 divided by 7,000 is just 11 sevenths. So 11 sevenths is equal to e to the 9 times r. And then we can go ahead and raise both sides to the 1/9 power to get rid of the 9. So 11 sevenths to the 1/9. That's equal to e to the 9r to the 1/9. And then if we use a property of exponents, e to the 9r to the 1/9 is e to the 1/9 times 9r, which is just e to the r. So just to summarize what we did here, I'll write it down here as 11 sevenths to the 1/9 equals e to the r. We want to know what r is. Okay, and we know how to do that because this is just an exponential equation. The base number is e. So if I convert this to a logarithmic equation, the base of the logarithm is e, and the exponent on e is r, so r is equal to the base e logarithm of this number, 11 sevenths to the 1/9. And we can verify it by using one of our tricks. The base e logarithm, so the base number e raised to the exponent r equals the argument, 11 sevenths to the 1/9. Okay, so these two equations are equivalent. This one is an exponential equation, and this one is a logarithmic equation, but this shows us what the value of r is. It doesn't show us what the decimal number is, but it's in a form that we could easily use a calculator to compute. The more conventional notation for the base e logarithm is the natural logarithm. So I'll just go ahead and write it using the base e logarithm. R is equal to the natural log of this number, 11 sevenths to the 1/9. And you probably have a high-powered calculator with the natural log function on it. It's just a key with ln.